In this lecture, you will cover how to optimize the parameters to train a segmentation model. Now, let's see what is the model optimization. So, the principal goal of machine learning is to create a model that performs well and gives accurate predictions in a particular set of cases. So, in order to achieve that, we need machine learning optimization. Machine learning optimization is the process of adjusting hyperparameters in order to minimize the cost function by using one of the optimization techniques. It is important to minimize the cost function because it describes the discrepancies between the true value of the estimated parameter and what the model has predicted. So for the model optimization, we need to define few things. For the model optimization, the first thing is to define the optimization algorithm with learning rate. Then we can also set the learning rate decay. And the third is the loss function that we need to define for the model optimization. So as we have seen, for model optimization, we need few functions, parameters, and hyperparameters. Before we go further, we need to understand the difference between parameters and hyperparameters of a model. You need to set the hyperparameters before starting to train the model. They include a number of clusters, learning rate, etc. Hyperparameters describe the structure of the model. On the other hand, the parameters of the model are obtained during the training. There is no way to get them in advance. Examples are weights and biases of neural networks. This data is internal to the model and changes based on the inputs. Now let's see what is the optimization algorithm. While training the deep learning model, we need to define each epoch's weights and minimize the loss function. And an optimizer is a function or an algorithm that modifies the attributes of the neural network, such as weights and learning rate. Thus, it helps in reducing the overall loss and improve the accuracy. Problem of choosing the right weights for a model is not an easy task, as a deep learning model generally consists of millions of parameters. It raises the need to choose a suitable optimization algorithm for your application. Hence, understanding this algorithm is necessary before having a deep dive into the field. So, an optimization algorithm finds the value of the parameters that minimize the error when mapping inputs to outputs. An optimization is a function or an algorithm that modifies the attributes of the neural network, such as weights and learning rate. Thus, it helps in reducing the overall loss and improve the accuracy. These optimization algorithms or optimizers widely affect the accuracy of the deep learning models. So there are different optimization algorithms that can be used depending upon your problem. So there is gradient descent, stochastic gradient descent with momentum, mini batch gradient descent, ADA grade, RMS prop, ADA delta, and ADAM. You can use different optimizers to make changes in your weights and learning rate. However, choosing the best optimizer depends upon the application. As a beginner, one evil thought that comes to mind is that we try all the possibilities and choose the one that shows the best results. This might not be a problem initially, but when dealing with hundreds of gigabytes of data, even a single epoch can take a considerable amount of time. So, randomly choosing an algorithm is no less than gambling with your precious time that you will realize sooner or later in your journey. What is learning rate decay? Learning rate decay is a technique for training and optimizing modern neural networks. It starts with a large learning rate and then decays it multiple times. It is empirically observed to help both optimization and generalization. An initially large learning rate accelerates training or helps the network escape spurious local minima, and decaying the learning rate helps the network converge to a local minima and avoid oscillation. To train a machine learning model, we must define a loss function in order to measure the difference between our model predictions and the label that we want to predict. So, what we are looking for is a certain set of weights with which the neural network can make an accurate prediction, which automatically leads to a lower value of a loss function. So, loss function is a method of evaluating how well your algorithm is modeling your dataset. Neural networks are trained using an optimization process that requires a loss function to calculate the model error. Loss function is used to quantify how good or how bad the model is performing. Dice loss and cross entropy are the two main types of loss functions to use when training a segmentation model. So, what is dice loss? The dice loss is a loss function that is commonly used in the training of semantic segmentation models that is based on the dice coefficient, which is a measure of overlap between two samples. Here you can see the formula of the dice loss function. Dice loss function is equal to 2 into A intersection B divided by A plus B. In this formula, A is the predicted segmentation and B is the ground truth segmentation. The dice loss ranges from 0 to 1, with the lower value indicating better performance. The main advantage of the dice loss is that it is differentiable, so it can be used with gradient based optimization algorithms to train a model. It is also a good choice for tasks where the distribution of the classes in the dataset is imbalanced, because it does not penalize false negatives as harshly as binary cross entropy loss. However, the dice loss is sensitive to outliers, so it may not be the best choice for datasets with high degree of noise. Pixel-wise cross entropy loss is a loss function that is also commonly used in training of semantic segmentation models. It measures the difference between the predicted segmentation and the ground truth segmentation by calculating the cross entropy loss for each pixel in the image. The cross entropy loss is defined in this formula. Here you can see the formula of the cross entropy loss. In this formula, n is the total number of pixels in the image, yi is the ground truth label for the ith pixel, and pi is the predicted probability of the ith pixel belonging to the positive class. The pixel-wise cross entropy loss ranges from 0 to infinity, with the lower value indicating better performance. The main advantage of the pixel-wise cross entropy loss is that it is a standard loss function for classification tasks, so it is a well-studied and has a good theoretical properties. It is also a good choice for tasks where the classes are balanced in the dataset. However, the pixel-wise cross entropy loss can be sensitive to class imbalance because it penalizes false negatives more heavily than false positives. So it can also be difficult to optimize for large datasets because it requires computing the log of the each predicted probability. So here is the model hyperparameters optimization code to train the segmentation model. You need to import the optim library, and then we have defined the optimization algorithm. Here you can see optimizer is equal to torch.optim.atom. So we have used the Adam optimization algorithm or optimization function, that is the most commonly used function. Then you can see we have passed the params is equal to models parameters, and also we have passed the learning rate is equal to 0.0001, and in the last line of the code we have defined the loss function. Here you can see loss is equal to dice loss. So in this lecture we have defined the model optimization hyperparameters to train the segmentation model. See you in the next lecture.